So again, welcome to the webinar. It will be about semiconductors and the thermal analysis of these semiconductors. So before we go on with the presentation, some organizational information for you. So all of you participants are muted. So if you have any questions, comments, or something else, please use the chat or the question answer tool. I will see the questions next to my screen, but I will answer all the questions then in the end after the presentation so that there will be a moderated question answer session. So also please use the chat in case of any problems. For example, if the presentation does not work, if you cannot see the screen or anything else, I will try to fix that as soon as possible. For your information, the webinar will be recorded, and after the webinar, you will get an email with the link to this recording and some further information to this webinar. Also, we are very happy to receive some feedback after the webinar, what you liked, what you did not like, what topics you would like to have to be discussed in a further webinar. So please feel free to contact us with some feedback. So I also want to introduce myself. So my name is Erika Hahn. I studied physics and I'm working for Linzai since 2020. I'm here responsible for the thermoconductivity and also thermoelectric measurements in our application lab. So you can also directly contact me if you have any questions. Yes, so this will be today's agenda. So first I will recap the topic semiconductors, then where semiconductors are used and how to characterize them. Then I will move on how we, with our Linzai instruments, can help with the characterization of semiconductors. Then I will also show some application examples, and in the end, I will summarize today's talk. For those who do not know Linzai Messgeräte is a company founded in 1956 by Dr. Maximilian Linzai. The company was founded in Selb in northern Bavaria. Now his son, Klaus Linzai, and his two sons, Florian and Vincent Linzai, are also leading the company. And we are a manufacturer of instruments for thermal analysis. We manufacture and develop everything here in Selb in our headquarters, but we also have some own sales and service locations in the US, China, and India, and more than 65 distributors worldwide, so that in almost every country you have a contact person which works with us. We, on the one hand, produce the instruments and also sell them, but on the other hand, we also offer some service measurements where we can test, for example, if the measurement instrument is suitable for the task, or if someone just wants to find out the properties of one material for one project, then it's of course not the best idea to directly purchase the instrument. Instead, one can use this service measurement service. So our product range is shown here on this slide. So it covers differential scanning calorimeters, TGAs, simultaneous thermal analysis instruments, dialectometer, some instruments for thermomechanical analysis, a broad range for thermoconductivity and thermal diffusivity characterization. We have also two instruments for the thin film characterization, also analyzers for thermoelectric properties, and the Hall effect device. In this range, we will have a closer look than later on. But what is unique for Linzai is that we offer a lot of customizations. So we always try to fit the needs of the customer, so to modify the instrument so that the application will be covered as much as possible. So let's start with the semiconductor topic. First of all, I want just to go through shortly onto the theory of semiconductors. I will just scratch a little bit on the surface of the theory, just to recap everything and that we all have the same level of knowledge for the later slides. Yes, so in general, there are three categories of materials. These are insulators, metals, and semiconductors. These can be distinguished on the one hand by the resistivity and the difficulty of passing current through the material under the influence of an electric field. So insulators have a resistivity at room temperature of about 10 to 12 ohm centimeter. Metals have a resistivity of about 10 to minus 6 ohm centimeter or lower. And in between those both, there are the semiconductors with typical resistivity at room temperatures from 10 to 6 to 10 to minus 4 ohm centimeters. Furthermore, the semiconductors and the metals can be distinguished as the resistivity is a temperature-dependent property. And for metals, this is only a weak relation. And typically, one can see that the resistivity is increasing with increasing temperature. Instead, for semiconductors, there is a very strong dependence on temperature, and the resistivity typically decreases with increasing temperature. So there's also a way to distinguish those two materials. However, one can also distinguish these three classes of materials in the band model. And the band model describes the energy states of an electron in the ordered crystal of a solid. And there are two important levels, which is the valence band, which is the highest occupied band. And there's also the conduction band, which is the lowest unoccupied state. In between, there can remain a range without any energy states. It's also called the forbidden region, and this is also called in the band gap. For metals, there's typically no band gap, and also it might be even the case that both bands overlap, so that there are always some electrons that can move freely. Because of that, they are also called the free electrons. And because of their free movement, the metals also have their good electric conductivity, because the transport of charge is only possible for a partially occupied state. Semiconductors have a rather small gap, so the electrons are still capable to overcome this forbidden region via excitation. This excitation can happen either thermally or, for example, by optical absorption. And once this is done, it can conduct. The excited electrons and also holes they leave in the valence band contribute then to the current flow. For insulators, the band gap is so big that the overcoming for electrons is not possible anymore, so that this forbidden region is just too large. Also here in this schematic, the Fermi level is shown. I just want to shortly explain that this is the limit up to which the energy levels of a system can be filled without gaps, without any thermal excitation, so at temperature 0 Kelvin. So from this filling happens from below, so from the energetically lower levels. Also, that you have a feeling what is a large gap, which can be or which gap is small enough to be overcome. So a band gap of about 3 electron volts can still be overcome by excitation. And some examples, well-known semiconductors like silicon have a band gap of about 1.2 electron volts. Gallium arsenide has about 1.4 electron volts. The insulator silicon dioxide has a band gap of about 9 electron volts. Furthermore, it is important to know that this distance of the energy bands is temperature dependent, so that the band gap typically decreases with increasing temperature. An important part of semiconductors is that semiconductors can be doped with different types and concentrations of impurities. And in this way, it is possible to select more or less and vary the resistivity of the semiconductor by ionizing these impurities. This ionizing typically happens thermally. One classifies here two types, the so-called N and P doped materials, semiconductors without any doping, so the pure semiconductor, are called intrinsic. To make this a little bit clearer, we have a look onto an example. This here is an example of silicon. So here you have the intrinsic case of silicon, where you see the silicon atoms and how they are bonded. For the case of an N-doping, one replaces one atom on the regular lattice side with an atom of a higher valence. For example, in the case of silicon, one can use phosphorus. The phosphorus atom doping leads into additional electrons in the conduction band. So here schematically is shown that there will be some further electron. The p-doping describes then the different side, so that one uses an atom with a lower valence. This can be, in the case of silicon, for example, be boron. And with the boron, there will be an additional hole inside the lattice. This is displayed here with the white part. So this doping also then affects the schematic of these energy levels. In the case of the N-doping, the additional electrons in the conduction band lead to the creation of a new energy level. This is then called the so-called donator level, ED. And this energy level is located right below the conduction band, and the ionization energy to lift an electron from the donator level to the conduction band is much smaller than the gap. As an example for silicon, this distance here is about in the order of 0.5 electron volts. Just as a reminder, the band gap is in the intrinsic case about 1.2 electron volts. For the p-doping, something similar happens, but the other way around. So the additional hole leads to a new energy level close to the valence band, and this is called the acceptor energy level, EA. In general, it has about the same order of magnitude as within N-doped semiconductors. So this should be just a short recap of the theory of semiconductors. Of course, the physical theory is much more deeper and much more complex, but this should be just an overview. So let's come to the point where semiconductors are used. So semiconductors are very essential for the electronics, where the possibility of doping especially is an important topic. Because of that, you influence the conductivity, and this is an important role for the design of electronical parts. The best known semiconductor materials are silicon and germanium. These are semiconductors consisting just of one element, and there are also, for example, gallium arsenide, indium antimony, or tin selenide, and so on. So there are a lot of semiconductor materials available, but the best known one is silicon. So semiconductors are important for the electrical engineering and especially for electronics, where this possibility of influencing the electrical conductivity by doping plays a very important role. So for example, the combination of differently doped regions, for example, in the well-known PN junction, enables both electronics components with a direction-dependent connectivity or a switch function, which can each be controlled by, for example, applying an electric voltage or current. So some examples here are diodes, transistors, or photodiodes. In general, semiconductors appear almost everywhere, especially in daily life, like in computers, smartphones, solar cells, in cars in general, especially hybrid cars, integrated circuits, diodes, and many more. So semiconductors are a very important kind of material, and they are used everywhere and especially in daily life. In recent years, silicon carbide and gallium nitride became of interest. These are wide bandgap power semiconductors, so that the band gap is so wide that it's really in the limit of which can be overcome by the electron with some excitation. The attention appears because the power semiconductors have significantly lower power loss compared to silicon-based power devices, so that these new power devices can improve the efficiency of the power supply and also lead then to the reduction of the size of an equipment. New power semiconductor materials are also expected to improve the fuel efficiency of a hybrid car and also to save energies of various devices, including something like electrical cars or trains, for example. Also, recently, organic, so primary carbon containing semiconductors are of interest and are, for instance, used as organic LEDs, the so-called OLEDs, or in solar cells. As the behavior of the semiconductor can heavily be influenced by the doping, it is also important to characterize the semiconductor as much as possible to be able to design electric devices as good as possible. So the characterization techniques for semiconductors are used to characterize semiconductor material itself or the complete device like the PN junction or a solar cell. The most used techniques can be grouped into optical, electrical, physical, and chemical. Just want to give here a short overview which techniques can be used for the characterization. So for the optical part, one can use microscope, one can use luminescence methods, different spectroscopy methods like Raman or FTIR. To the physical and chemical characterization techniques belong, for example, electron beam techniques like SEMs or ion beam techniques. There are also some spectrometers which can be used. Chemical etching might be of interest for the characterization, and also some further physical properties like thermoconductivity or the thermal expansion belong here as well. For the electrical characterization, especially the electrical conductivity and resistivity are interesting properties, as well as the carrier concentration, especially in the doped case of semiconductor. There is also the mobility, which is of interest, and the Hall coefficient is also often characterized property. So in general, the characterization of the properties of the raw material and also the device is important, as the properties can vary strongly with doping, but also with temperature. And in the next slides, there are some examples. So for example, the thermal conductivity. In general, the thermal conductivity of a semiconductor depends mainly on the thermal conduction by phonons and the mixed thermal conduction by free charge carriers, so the electrons and the holes. There are also some lattice contribution of thermal conduction. It occurs through, for example, diffusion and scattering of phonons. Scattering events include, for example, phonon-phonon scattering, phonon defect scattering, and scattering between phonons and charge carriers, boundaries, or surface scattering. In general, the thermal conductivity strongly depends on the doping concentration and also on the temperature, as shown in these two examples. So here you see the thermal conductivity independence on temperature of gallium nitride, the intrinsic case, the undoped one, and the doping with silicon. Here you can see that the intrinsic one has the highest thermal conductivity, and dependent on the doping concentration, the thermal conductivity can drastically change. Also, one can see a clear dependence on temperature. So this is why it's also important to perform a temperature-dependent analysis. On the right, you can see here the thermal conductivity, also dependence on temperature for various materials. Also, copper is shown here, and silicon carbide, gallium arsenide, and silicon are shown, where you can especially see that all of the curves have in general a similar shape, so that first the thermal conductivity is increasing. At some point, the maximum is achieved, and then for increasing temperature, the thermal conductivity decreases. So one can here clearly see that the thermal conductivity depends on temperature and also on the doping, kind of doping, and also on the doping concentration. Then, as a second example of why the characterization, here the electrical characterization is an important task. The electrical properties also depend strongly on the doping concentration and on the temperature. Here is an example of the mobility of electrons and holes in silicon and dependence on temperature. So here's the mobility, here's the temperature, and one can clearly see that the mobility changes with temperature and also for different concentrations. On the right, you see an example of the resistivity and dependence on the doping concentration at room temperature. So here only the resistivity and dependence on the doping concentration is plotted, where you can see that the N-type and P-type doped silicon behaves differently, but clearly both depend on the doping concentration, so that the higher or the more impurities are brought in, the lower the resistivity will be. And here also for the gallium arsenide case, here even the N-type and the P-type differ more strongly in resistivity, but both also show a clear dependence on the doping concentration. So hopefully it should be clear right now that the characterization of semiconductors is an important task, as especially the doping concentration and the type of doping can influence the behavior strongly. Furthermore, the analysis should be also performed in dependence on temperature, as here also different behavior is observed. For the electrical characterization, I also want to recap shortly the different types of methods which are typically used. So typically the electrical properties are determined either via a 2 or a 4-point probe method. These are each shown here schematically. So the electrical conductivity, which is the product of charge mobility and charge carrier concentration, is mostly determined using here the 4-point probe setup for contact needles more or less separated in the same distance are placed on the sample, and the current and the voltage are tested at different probes, whereas in the 2-point probe setup, both are used with the same contact needles. However, in most cases, one finds out the electrical properties using a Hall effect measurement setup. This brings the advantage as the charge carrier concentration, the mobility, and the resistivity can each be determined individually and not as a product as with the 4-point probe setup. So then one here has all single properties individually as a result. So this is the schematic Hall effect measurement setup, so that one uses more or less also a kind of 4-point probe setup, but additionally one applies a magnetic field to the sample to investigate the properties. Furthermore, the Hall effect measurement setup brings the advantage that one can find out the behavior of the material in a magnetic field, especially as in very strong magnetic fields, one can detect a significant increase of resistivity. This is the so-called magnetoresistance, and this can be also found out with the Hall effect measurement setup. So now let's focus on how Linsize and its instruments can help with the characterization of semiconductors. So which kind of instruments are of interest when there is the task to characterize a semiconductor. On the one hand, one might be interested in the specific heat capacity, for example. This can be realized with a DSC, so a differential scanning calorimeter. Additionally, one can find out some phase changes of the material if there are any. A further probably interesting instrument is the dilatometer. Here, the thermal expansion and the so-called coefficient of thermal expansion, shortly CTE, can be determined. However, these both types of analysis, so the DSC and the dilatometer, are not the main focus of the characterization of semiconductors. I just wanted to mention them right now, but I will focus more on other properties like the thermal conductivity and thermal diffusivity. This is an often requested property of semiconductor materials. So in the next slide, we will have a closer look onto these instruments. But in general, with these instruments, one can find out the thermal conductivity and diffusivity of a broad range of materials, from bulk materials to thin films. The thin film instruments also lead to the figure of merit, which is an often used property for also thermoelectric materials. To the main thermoconductivity instruments for the analysis of semiconductors, these four are important. So Linsize also offers further instruments for thermoconductivity, but in the case of semiconductors, these are the four most important ones. So this is the laser flash, shortly LFA, the periodic laser heating method, the thin film laser flash, and also the thin film analyzer. And in the next slides, there will be some more details to each of the instruments. So starting with the laser flash analyzer, shortly LFA, it is a measurement instrument according to ASTM norm, the E1461 norm, and it measures the thermal diffusivity and also thermal conductivity of typically a bulk material. So with a thickness of, let's say, about 0.1 millimeter to 6 millimeter, the property can be determined. So it allows the broad thermal conductivity range analysis from very low conductive materials to high conductive materials, and the analysis can be performed also in a very broad temperature range, also above the typically for semiconductor interesting temperature range, even to about 2800 degrees Celsius. The samples typically have a disc shape or a rectangular shape in the order of about 10 millimeter to 1 inch. And the sample preparation is quite easy. You prepare your sample according to the requested size for the sample holder, and then both sides of the sample are covered with a very thin graphite layer. The use of that I will explain in a minute. And then the sample will be just put into the sample holder and then into the sample robot. The LFA allows the measurement of up to 6 samples at the same time so that there's a high throughput of samples. The method works the following. So you have a power source. This is, in our case, either a xenon lamp or a laser. The power source shoots a short, high intensity energy pulse towards the sample. The sample absorbs then the energy, and a part of it is emitted as infrared radiation on the Earth surface of the sample. This radiation is collected via an infrared detector, and in the end, we will obtain a signal which looks like that, so that we can see here the temperature rise with time due to this short laser pulse put onto the sample. The graphite coating is used as the absorption of the energy will be then maximized, especially, for example, in the case of a metal with a shiny surface. This black and matte surface helps a lot with absorption. From this curve, one can obtain then with some models the thermal diffusivity according basically to this formula, so that the sample thickness is also relevant for the analysis. I do not want to go too much into detail of the instruments. This should be just a short overview on what instruments might be capable of characterizing a semiconductor and shortly describe how these work. So this setup is put then vertically into our instrument so that the energy source is on the bottom. The sample robot with up to 6 samples is located in a furnace, and here on the top is the detector. I mentioned that the sample thickness can go down to about 0.1 millimeter. If one has a material with a lower thickness, one can, for example, use the periodic laser heating, shortly PLH. This is a new technique with a brand new instrument we offer. It is especially useful for thin samples, lower than 1 millimeter, maybe down to about 20 micrometer thickness, to be able to determine the thermal diffusivity. Sample size and sample preparation are similar to the LFA technique. Also, the general setup is similar, as you can see here. The main difference is that we use a modulated laser with a certain frequency, and because of that, also the infrared radiation emitted at the rear surface of the sample will be also a thermal wave with the same frequency as the modulated laser light. This we also collect with the infrared detector, and in the end, the signal will look like that. The IL curve is symbols the modulated laser light, and the second curve, the IIR, is the signal of the sample. The frequency is the same. However, one can observe a phase shift, and one can detect a difference in amplitude. This is then plotted in a certain way so that in the end there will be a linear relation. These linear relations from the phase and the amplitude, we find out the slope of this plot here, and this slope will be in the end used for the thermal diffusivity calculation. For the thermal diffusivity calculation, also here the sample thickness is an important parameter. Here maybe the question arises why thin film thermal conductivity needs to be separately typically analyzed. The main difference is also that thin film materials behave differently, like bulk materials, as parasitic surface effects are much stronger due to these smaller dimensions and the high aspect ratios. Furthermore, there's a stronger influence on surface scattering and boundary scattering, and the transport properties will just change due to the different thickness, so that it's also an important task to find out the properties of the bulk material and of the reduced size, as it is plotted here, that the thermal conductivity significantly reduces by reducing the thickness of a material. For these tasks, especially when going down to low micrometer and nanometer ranged thicknesses, we have to further special setups. So on the one hand, the thin film laser flash, it is especially relevant for multi-layer samples and for semiconductors on substrate. It also allows the determination of thermal diffusivity and thermal conductivity. The sample preparation is a little bit more complex here, as it is required to put a thin gold layer on top of the sample so that this will be a reflective layer, as the method uses the thermal reflectance of this gold layer to find out the thermal properties of the underlying layers, also using here a multi-layer evaluation model to be able to model all those used layers in the sample. The setup in general works similar also to a laser flash, so that there will be a pump laser heating up a small spot on the sample, but we do not use an infrared detector here to find out the response of the material due to this heating, but we use a second laser, the probe pulse, which uses the thermal reflectance of the gold layer to be able to evaluate then the behavior of the complete setup. In the end, we will also have such a falling edge, similar to the classical laser flash setup. The second thin film instrument for finding out the thermal conductivity is the so-called thin film analyzer. This setup is a modular setup, so one can also use some further tools to be able to measure not only the thermal conductivity, but also the specific heat capacity, the electrical properties like conductivity. One can also upgrade the instrument so that the Hall constant can be measured. Also, the Seebeck coefficient can be determined, and, for example, also the charge carrier concentration, so that in the end, the often requested figure of merit can be determined with all those properties, and additionally, the Hall constant. The measurement method uses a chip where these pads are all used for the measurement. So it's an integrated characterization system with this chip where you directly evaporate the thin film onto it. It's especially for very thin films in the low nanometer to about 25 micrometer range. And yes, so the properties are determined using a 4-point probe setup, and the thermal conductivity will be determined with the 3 omega method, and all the properties determined are in-plane properties. That's also an important point here, which needs to be mentioned. Yes, so the thin film analyzer is more or less an instrument for the complete analysis of a thin film regarding thermal conductivity and thermal electrical properties. So as mentioned some slides before, especially the thermoelectric or the electrical properties of a material or a semiconductor are of main interest, as these can be heavily influenced by doping, and these are the most important properties for the design of electrical devices. So the next slide will show the instruments which can be used for the characterization of electrical properties like conductivity, resistivity, the Hall coefficient, mobility, and charge carrier concentration. The first instrument here is the LSR3. It allows the determination of the conductivity, resistivity, and the Seebeck coefficient of many materials. It is especially suited for the analysis of bulk samples. So typical sample sizes are bars with a diameter of 4 millimeter and a length of 15 millimeter. However, there are also some adapters for thin films. So either thin flexible films or thin films on a substrate. There are also different furnace options to cover a broad range of different temperatures. And this instrument setup uses the 4-point probe setup. So we have 2 electrodes where the sample is clamped in between, and we have 2 probes which touch the sample from the side. So here you can see a photo of the real setup. And based on this 4-point probe setup, then the resistivity is determined. So that here the sample size or the cross-sectional area as well as the distance of the probes is needed for the resistivity determination. To be able to determine this distance of the probes as exact as possible, there is also a camera option with which one can very accurately determine the distance of the tips here. As mentioned, the LSR3 can also determine the Seebeck coefficient. Here, the same setup is used. However, one does not imply a current into the material, but one creates a temperature gradient over the sample. For that, in the lower electrode, there's also a secondary heater, which creates then this temperature field along the sample. And with the probes, we determine then the thermal voltage, which results of that. For more challenging samples, there are also some further options like a high resistance option. There are different thermocouple types to avoid any reaction. And in the case of thermoelectric analysis, there is also a Harman add-on to be able to directly determine the figure of merit. There's also the so-called LSR1, which stands for Lindsay Seebeck and resistivity meter. It is a very compact desktop setup and looks like that. It can also determine the electrical resistivity, conductivity, and also the Seebeck coefficient. And the setup is especially suited for the analysis of thin films on a substrate. The electrical resistivity is determined using a 4-point Van der Pol setup. We use here such sample boards where you place the sample on top and contact the sample with these 4 needles. The sample holder for the Seebeck coefficient looks a little different, where you put the sample on top and there is some thermal couple wires touching the sample to be able to find out the Seebeck coefficient. So these are 2 instruments for the electrical conductivity determination, which might be of interest. These sample boards we also use in our Hall characterization system, shortly the HCS. Here, then, of course, also the electrical conductivity and resistivity can be determined. Also, the same sample board as with the LSR1 can be used for the Seebeck coefficient determination. Difference to the HCS is that there are also different magnet options available, so that also the Hall coefficient can be determined, also using here the Van der Pol equations, where we get then in the end the Hall coefficient, the Hall mobility, the type of the charge carrier, indicating the plus or minus sign of the Hall coefficient. Then we can find out as well the charge carrier concentration. Sheet resistance can be determined, as well as the magnetic resistance. Also, as the LSR1, the HCS is especially suited for the analysis of thin films on a substrate, but it is also able to measure bulk materials. Yes, one point which should be mentioned together with the Van der Pol method. This method allows also the analysis of samples of arbitrary shape. Due to this Van der Pol setup with this 4 contact needles. The Hall characterization system has different exchangeable sample holder boards. So for different sized samples, also for the Seebeck coefficient determination, and there's also a high temperature sensor with which one can heat up to 600 degrees Celsius. The classical boards can go up to about 200 degrees Celsius. The Hall characterization system can be equipped with different magnet options, like a permanent magnet, electromagnet, or a Hall-Bach magnet. Furthermore, what should be mentioned here is that one can also use DC or AC magnetic fields. The AC magnetic fields are especially suited for materials with a very low mobility, below 1 centimeter squared per volt second. Because here the DC method just comes to its limits. So this can be also equipped with our Hall characterization system. Also, the HCS and the LSR1 have the possibility of a further option, the elimination option, where it is also possible to investigate the optical excitation in the semiconductor. So we're coming now a little bit to the end. And the next slides, I want to show just some application examples of semiconducting materials we already analyzed. So here you can see the analysis of a thin film of bismuth antimony with a thickness ranging from 84 to about 280 nanometers. And this analysis was performed with the TFA, so that the full analysis was possible. Here you can see the electrical conductivity, the thermal conductivity, Seebeck coefficient, and the Hall constant in dependence on temperature. So you can clearly see different behaviors of different sized films, and also the behavior changes with temperature. Furthermore, also the material behaves differently in dependence on if you are heating up or if you are cooling down the material. So with these instruments, a lot of analysis can be done, so also testing different requirements. Here you can see a measurement of a silicon germanium alloy measured with the LSR3. So here a rather bulk sample was used to investigate, and clearly the resistivity changes with temperature. Analysis with different instruments was performed on an N-type and P-type bismuth telluride samples differently doped. The electrical resistivity and conductivity, as well as the Seebeck coefficient, were measured with the LSR system. The L of A determined the thermal diffusivity, the DEC, the specific heat capacity. The combination of both led then to the thermal conductivity. Here in this example, you can clearly see that the N-type and the P-type material show completely different values and also different behavior with temperature. Here is also an example performed with the Hall characterization system. Also, a bismuth antimony thin film was measured. So the Hall coefficient and the mobility were tested, as well as the resistivity, dependence on temperature, both or all of those properties. And there's also an example of indium tin oxide with a thickness of 185 nanometer. This was also measured with a Hall system from room temperature 200 to 200 degrees Celsius. And here one can see the Hall coefficient does not change that much with temperature. However, the mobility and resistivities show a stronger dependence on temperature. So these were some examples, and now I want to come to an end. So in summary, I showed you the semiconductor materials and how to analyze them. It is important to analyze them because semiconductors show a broad variety of electrical resistivity and conductivity, as well as thermal conductivity, for example, because these properties are heavily influenced by the possibility of doping, and also the properties change with temperature. Linsize offers for that a broad product range to cover a lot of different applications and to be able to analyze different materials, so bulk to thin film, in as broad temperature range as possible. Some properties which can be determined, just to quickly summarize, are specific heat capacity, thermal expansion, thermal conductivity and diffusivity, and electrical conductivity and resistivity, as well as the Hall constant, and by that the found out properties like mobility or magnetoresistance. And there are special setups for thin film analysis. So if you have the task to analyze a semiconductor, please feel free to contact us, and we will help to find the right instrument for you, which can cover your application. So at this point, I want to thank you for your participation and your attention.